All right, everyone. Welcome to our second Training in Code Performance and Scaling webinar. I'd like to introduce Dr. Lars Kostriki from the Texas Advanced Computational Center, who will give you the details on the code performance and scaling, and myself, Ken Hackworth, from the Pittsburgh Supercomputing Center, and I lead the allocations group in Exceed. So why don't we go ahead and begin? A couple housekeeping notes. Through the session, we will accept questions through the chat boxes as appropriate. We'll take time to answer those, sometimes through just chat or sometimes verbally. We also ask you to mute yourself. We will mute you for you also, so that we don't have any interruptions at all. So on to the session. So since this is an Exceed related event, we have a code of conduct in Exceed. We'd like to follow this. We hope everyone enjoys our session, but follows our code of conduct. There's more details here at the site that's on the Exceed site about the code of conduct, but we just hope that we're all enjoy our webinar and we can proceed with no issues. On to the next. So Exceed, the extreme science and engineering discovery environment, our mission to substantially enhance the productivity of a growing community of scholars, researchers, and engineers through access.
You're looking at it anyway, right? Just
okay. I'm sorry, I'm going to mute a couple people here. Thank you. Yes, so let me start. To substantially enhance the productivity of a growing community of scholars, researchers, and engineers through access to advanced digital services that support open research and coordinate and add significant value to the leading cyber infrastructure resources funded by the NSF and other agencies. Next slide. So these digital services provide users with a seamless integration to NSF's high-performance computing and data resources. Exceed's integrated comprehensive suite of advanced digital services combined with other high-end facilities and campus-based resources serve as a foundation for a national cyber infrastructure ecosystem. So one thing I'll mention about the digital services, you probably will see some new resources coming online in the Exceed portfolio in the very near future. So be aware, there's two new resources that are coming online in this current submission period, the Expanse system from SDSC and the Bridges 2 system at PSC, as well as a few others later in 2020 and in 2021. So yeah, it'll be an exciting time with lots of new resources for the community. So how to connect to these digital services or the resources. So again, the PSC has this, the Exceed has this diverse portfolio of allocated resources, you know, big HPC systems, high throughput systems, GPU and AI systems, visualization systems, large memory systems, a lot of data storage, cloud systems. And again, here, Dr. Kostriki is part of the ECSS group, as well as there's a group called the SGCI, Science Gateway Community Initiative. This is a resource of people that can help you do better on the resources that you're using. So this is part of our task to provide some information about code performance and scaling, which is a mandatory document in a research request. So what we provide are, for most US-based researchers at no cost allocations via Exceed, is to be able to get a startup allocation. These are precursors for research allocations to do benchmarking, porting, testing, and also that you can prepare yourself for making a larger production request, this being a research allocation. We're currently in a submission period now that will end July 15th. So if you're here for that, thinking to improve on your documents that you'll be submitting, this is the best place for you. Okay, next slide. So why request a startup allocation? And I covered that quickly. So again, requests are accepted at any time. There's no deadlines for these. So if you don't have one now, go ahead and submit a startup allocation. We get you on these resources pretty quickly. These are reviewed in less than 2 weeks, usually a few days. I think our average is 7-day turnaround. All the Exceed resources that are currently in production can be requested Simple as an extended abstract and a PI for the CV or the co-PIs. The purpose of the small scale computational activities, application development, benchmarking, evaluation, and again here to prepare to submit for research allocations and getting better understanding of code performance and scaling. Research allocations, again, there's an open submission period now. These are for projects that have progressed beyond a startup phase. This is where you're getting into production usage. You know, we think of small as being a couple 100,000 compute hours up to tens of millions of compute hours. These are reviewed quarterly by an XRAC panel of peer reviewers, one award per research team. It's very highly competitive process. We see on average 200 plus proposals per quarter. So proposal quality really matters. 80% of our proposals are awarded, but a large number decline because of poor code performance and scaling. So something we saw is 32% of the new proposals in the last year were rejected because of the code performance and scaling information. It's just not sufficient. So that's why we came together, Allocations and ECSS, to put this talk on so that you all can do better and have a better chance of getting a larger or an allocation accepted in the XRAC area. So I will turn this over to Dr. Kostriki, and he will continue with this webinar. So thank you, and feel free to ask questions in the chat box, and we will go from there. Thank you. It's all yours, Lars. Thank you.
Yeah. Hi, everybody. My name is Lars. I'm a longtime member here at the Texas Advanced Computing Center, and I'm a longtime reviewer. So I tried to put this together with a lot of hands-on advice. Of course, we cannot cover all the corner cases. It is more important that you kind of understand the spirit of how the review process works and what you have to look out for. So the first thing is that the well-justified computational plan is taking front and center in your proposal. When most PIs, when they ask for computational time, they have, of course, already funded projects with NSF or NASA or DoD, etc. And so in that case, the science is not reviewed per se. Nevertheless, your computation should match the science of the project. And so what the reviewers are looking out for is not the science and how important it is how well you demonstrate that you are competent in using these expensive resources, and therefore that is what you have to do. And I will tell you what a well-justified computational plan is in a second, but in the hands-on advice here, you can already see what it is not. It is not your NSF proposal plus 2 sentences, or because my science is so important, please give me 1 million SUs. That is where you run into trouble. So when you ask for a startup, and I don't have to go through the details again, the entry bar is pretty low, and you get a generous amount to get started, and you will use those SUs to build up your computational plan, and then you submit on a quarterly basis or your full proposal. And when you write your proposal, like always with every proposal writing, it is full of common sense that the things that you have to consider. If you are new to the process and you are new to the review panel, then of course, like in any other review, you are under more scrutiny than proposals that are from well-established groups. Groups that are well established certainly have also a better chance of winning very large awards. So new PIs have to establish a track record first. So you start smaller, and then if necessary, you can build up in size. What I always tell new PIs, you have to compare your request size to the total availability of the resource. And that is not something that we publish, but you know how many hours there are in a year, you know how many nodes are available in the resource that you are asking for, and you can have a rough idea of how many PIs you may have on those resources, usually of the order of hundreds. So you have to limit yourself to a reasonable fraction of the target system. If you submit a smaller request, certainly the scrutiny is less than for larger requests. So if something is missing or if your scaling doesn't look as convincing, with a smaller request, you get more easily away with that. Focus on what you really need. One resource or a few, whatever you need, but don't target similar resources without a good reason. And I have highlighted here 2 reasons that are not very, very good. Convenience is not a good one. And also, what if a system is down? Our resources are up, have a high percentage of up. Young is asking if you have 2 research projects, you will always ask apply only for one allocation, and then you will outline both research projects in that one proposal. Otherwise, we would have too many proposals to review, and it would be just too much extra work. So 1 PI, 1 proposal, or 1 PI, 1 project. Okay, common sense when preparing your proposal, reasonable request size, internalize that there is a fierce competition for the resources. So a better proposal pays off, a not so good proposal may be rejected, and then you have to go back to the drawing board and come back in 3 or 6 months later. And also overly ambitious proposals do not fare that well. So what makes a good proposal? You're competing with many others, and writing a better proposal is certainly worthwhile doing it. So the basic outline is here on the left, and you have to focus on the computational plan, and the rest of the talk is all about that. And then a proper estimate of how many service units, how many SUs you need. And if we look at the details, some of the details here, your proposal is comparable to an NSF proposal, but it has a quite different focus, namely the computational plan. And you also have to keep in mind that the reviewers are not necessarily domain experts in your field. So a broader approach when explaining the science or the scientific question is always appreciated by the reviewers. So if your project is in chemistry, the reviewer will not necessarily be an expert in the subfield where you are an expert. It will be a fellow chemist. So keep that in mind when you're explaining that. You, of course, connect your scientific questions to the computations that you are proposing. You outline a little bit what equations or algorithms are being applied, how the code is parallelized. You describe the software, the tools, programming environment, anything that is applicable here. And you do that to assure the reviewers that you know how to run the code on the target system. And ideally, you had the startup on the target system, and you use that information in your proposal. And then you have a computational plan. You tell the reviewer how many calculations you want to do, how many nodes it uses, what the runtime is, and so on, and so on. And you add some basic math where the reviewer can verify your calculation, your estimate of the total SUs. And number 5 and 6 are the most important points here. You also will provide scaling data, and the scaling will show to the reviewer that you know how to efficiently use the resource. And based on your scaling, from these scaling plots, you will justify the size for the calculation, the node count, the core count for an individual calculation, based on scaling efficiency, total runtime. And as always, reviewers will appreciate all organized efforts that you do in that area. You have all been reviewers yourself. The more organized the proposal is, the easier it is to review, and that certainly skews the verdict into a more positive range. Yeah, hands-on advice, the computational plan takes center stage. Therefore, it's not just a terse sentence, and therefore we request some million SUs on the resource. The reviewers want to be assured that you know what you are doing. So how do you actually do that in your proposal? And what we do is we are using a crutch here. We are using scaling efficiency for two purposes. One purpose, we go into the first purpose here. We use it as a proxy to see how efficient, to judge the efficiency of an application. We all know and acknowledge that that is that is not the most appropriate way to do it, because there are different codes, different algorithms, and so on and so on. But if you would really like to go into the depth into how efficient an application is, that is a research project in its own. So we use scaling efficiency as a proxy, and that's why it is so important that you provide the review panel with scaling data. And they want to see the scaling on a target system or on a similar exceed system. So if you use an HPC cluster with normal nodes and no add-ons, then it may be okay if you do the testing on a Pittsburgh node and then you ask for time on a node in San Diego. But it is usually better if you really use the target system. Of course, if you want to use GPUs, then you do your scaling data on GPU nodes, stuff like that. And of course, you cannot cover everything. So you have to present scaling for a typical case, and then from there you have to make your argument. You present timings for a few time steps, timings for a smaller sample. If you have a more complex situation like AMR, you have to use a simplified setup and discuss all that comes with it. And then your documented scaling should either cover the number of nodes that you're actually targeting for production, or you apply a well-justified extrapolation from a smaller sample or fewer time steps. Certainly you should target a node count for production where your scaling is good, and there will be some plots in a minute. And you balance wall clock time and scaling and parallel efficiency. So your allocation is for a year, so there is really no point to say, we want to scale further out. We acknowledge our efficiency is not as high, but we want our calculation done in a month. Raul asking, should I also specify the typical number of nodes used for typical run? Yes, of course. And I have examples for that as well. The reviewers want to see where's your scaling good and what node count do you pick, so that they can verify that you actually picked a good spot. Oh, that is too long for me. I think Ken is going to pick this next one up. Okay, speed up and parallel efficiency. This is slide 1, and first we talk about strong scaling. And in strong scaling, the workload is kept constant even as you throw more resources at it. And so if you use more resources, then ideally you expect that your execution time decreases with the number of resources. Now, if you plot it, or if you calculate the speed up, that would be the ratio of execution times, like T1, the time it takes on one core or on one node, divided by the time it takes on n nodes. Here, in this setup, your strong scaling is linear. I have a plot on the next slide, and therefore easy to assess. Don't use the inverse, or don't use the time itself, because then you have a plot that is 1 over x, and then everything is much more different and difficult to judge. Note that strong scaling experiments on a single node will always flatten out at some point because you will run out of memory bandwidth. Often strong scaling experiments are conducted for smaller calculations. So here is what a typical or idealized scaling could look like. We plot the speed up versus the cores or nodes. The ideal scaling is now a linear plot, a linear curve. And now you're in orange here, that is what you have measured. And here you can see where you hug the ideal scaling, you are in good scaling regime, then there's some reasonable scaling. And then when your speed up turns over, that's of course the regime of bad scaling. And a beginner mistake is, of course, to pick the maximum speed where the wall clock is shortest. That may be the most advantageous for you, but the efficiency is already very low, so you should not pick that. So if you pick either linear axis or log, then you have a linear ideal curve, and everything is just fine. And if you do something that is 1 over x, like here on the right-hand side, then it's hard to see where your scaling is good, where it is not so good, and where it is bad. Reviewers are reviewers. They are like you when you review other proposals. If you make it difficult to review or to figure out if the numbers make sense, and the reviewer has to put in a lot of time to take measurements from your curves here and do some math, then the reviewer is more likely inclined to severely cut or even reject your proposal. This is even more severe if a reviewer becomes suspicious that you have chosen a scale that is difficult to assess for reasons that are a little bit fishy. So therefore it's much better to be open and to make it accessible to all the reviewers. So the other part is when we talk about weak scaling here, and there we use something different, which is called parallel efficiency. And now the workload is proportional to the amount of resources that are being used. When you use twice as many resources, you make your problem twice as big. That means ideally, if you had perfect scaling, your execution time stays constant with the number of resources or the problem size. And now we define parallel efficiency where you divide the time it takes on one node, and we divide that the time it takes on n node. If your parallel efficiency is 100%, then that ratio would always stay 1, or certainly at some point you will pay a price for using more and more nodes. So your time in the denominator will get longer, which means now your ratio will be below 1. It's often, these experiments are often conducted for larger calculations on multiple nodes. In some fields, it's also common to use progress rather than execution time, like the simulation time or the time steps per hour or the simulation time per second of your compute time, like femtoseconds per second in molecular dynamics. I personally think that is all fine, but do not confuse the reviewers. Explain a little bit what the unit is and why it makes sense. If you are in molecular dynamics, this may make perfect sense, but other chemists who may work in a completely different field need, it doesn't hurt to put a little refresher in why you think this unit makes sense. So an idealized scaling plot looks like this. We do nodes, either on a linear or log scale, depends how large your range is. We have the parallel efficiency here. Ideal is 1, and there will be a regime where you're not deviating much from 1, then it turns over, and after that it declines. So your parallel efficiency is the ideal time over the actual time. And the ideal time is the time on a single node or on a small number of nodes, whatever is more appropriate. Yeah, that is this time here, a point here, or the time on the smallest number of nodes that is feasible. Of course, for some problems, you cannot make your baseline so small sometimes that it fits on a single node, so you may have to start on 4 nodes or on 60 nodes or things like that. And that is all fine. If you do that, just explain a little bit why you have to do that. And now, when you have your scaling plot done here, like here on the right-hand side, at some point you have to pick, which node count do I really want to use for my calculation? Again, common sense. Particularly for large calculation with a high SU consumption, do not target quick completion at the expense of efficiency. The goal is to demonstrate that you will use the resources efficiently, and if you pick something that is too far out, the reviewer will not believe you. The award period is for a year, so so everybody expects you to run through your allocation at some more or less constant burn rate through the whole year. For very small proposals or allocations, that is of course different. But for your proposal, do not push it too far out here to the right. Of course, non-ideal scaling is a fact of life, and you find a good compromise and you present your data, as always, in a favorable way. That's how we all write proposals, but you have to be transparent so that the reviewer is not getting suspicious that you're withholding some important information from them. More hands-on advice: balance efficiency and runtime. Stay on the efficient side. Allocation is for a year. Reduce wall clock time by advancing multiple calculations simultaneously, if that is applicable. For very long single calculations that need a lot of, where you burn a lot of SUs through the year in one single calculation, keep in mind that for every 24 hours of your job running, there has to be a queue time. So if you're proposing a project where a single calculation has to run non-stop for 365 days in a year, the reviewer will reject that because that is not feasible. Because, I mean, 1/3 of a year, that is already a stretch. So keep that in mind as well. If you have time-critical projects, what comes to mind is often weather forecast. You can push a little bit farther there, of course, but in the end, if you're pushing for 20% wall clock reduction and at the price of doubling the number of resources, that is a regime that is difficult to justify. If you're pushing too far, you will be told to optimize your applications, or you may receive a severely reduced allocation. And also important, if you have small but numerous calculations, then investigate how you can bundle multiple calculations on a single node. In many centers and many machines, the nodes are not shared. So if a single calculation is using only one core, you cannot afford to leave all the other 50 cores idle there. Investigate that and present the most efficient setup. Now, we have only talked about parallel efficiency to convince you, the review panel, that you know how to operate the machine and that you pick a good number for the node count. But part 2 of this is, and that may even be more important, is that you will use your scaling data, the test numbers, the performance numbers that you get out of it, to accurately estimate the number of SUs that you need on that target system. So when we are here in our diagram and we picked up here, okay, we want to use these, this is the node count that I want to use. And from your benchmark calculations, you know how much time it will then take. Now you can put it all together and you can present some simple math to estimate the total request. I have one question from Young here. A Volta with 16 GPUs, if I use 5 cores per GPU, how many SUs is it? That is all outlined in the user guide. So GPU nodes are sometimes not shared, or your cost is per GPU that you are using. But that is all outlined in the user guide, and it's of course then your responsibility to figure out what these numbers means and how to make a proper estimate of the SUs. So you present simple math, and I have a table on the next slide how you may do that. You use the timing from the scaling experiment. You extrapolate towards the total number of time steps or individual experiments. You present all the details for all planned experiments. You allow the reviewer to easily follow your estimate. That's the simple math. You give the reviewer reassurance that your estimate is not bloated. And me personally, as a reviewer, I always like a table. So that is the easiest. If there's a table for the estimate of the SUs, that may be the first thing I read when I do a review, just to get an idea how many experiments are there, how big are they, how big are they, and what's the total number of SUs. If you do parameter studies, and it is important that you highlight that you have selected a reasonable or a small number of parameter combinations. And I always find it helpful that you discuss how first results may inform the selection of other parameter combinations in the future. Of course, don't forget to justify storage. So this is my example with my example table. So the simple math for every experiment and method is the number of nodes and cores that you want to use times the total runtime times the number of simulations, that is your number of SUs. And keep in mind, on some systems an SU is a core hour, on some systems it is a node hour, and if you have a if you're targeting GPU nodes, then those may be even in a third category. From the scaling, you justify the number of nodes or cores that you want to use. And from the scaling and performance data, you map simulation time to total runtime. So the number of cores here, they come from your scaling, and the total runtime comes also from the scaling and the performance data. So when you create this data, you use it twice. And the resolution and the simulation time, how long your molecular dynamics has to run, or your simulation and astrophysics, that is justified in the rest of the proposal, the sciencey bits that are there are. Yeah, Paul Robustelli has a question. Yes, if you are on single GPU nodes and you do not have to communicate between the GPUs, therefore you say a simulation length times number of GPUs, then in that case you will calculate the total number of SUs by saying each experiment has a total runtime on a single node or on a single GPU, and I want to do a number of simulations, and you get your total number of SUs. And then you say that the number of nodes or GPUs that you're targeting is 1. And then later on, once you have your allocation, then you can decide if you run jobs with one calculation on one GPU, or you bundle your calculations up and you run a job that runs on 4 GPUs and advances 4 calculations at a time, and so on and so on. That just depends on what the queue looks like and how much you want to push. But if you need only one node, because you have embarrassingly, or we call it now, of course, conveniently parallel computations, then you would have made the argument in your scaling document that you only need one node, and therefore there's a 1 here in this calculation. Yes, so you use the scaling for the number of nodes and cores. If you don't need scaling, that number is 1. You use scaling and, in this case, performance data to map simulation time to total runtime, and you justify resolution and simulation time by the sign bits. And here in my table, I made up some examples where I characterize the experiment, fluid 1, fluid 2. I have some method, explicit 3D, implicit 3D. I made this all up, or molecular dynamics, size, simulation time, number of nodes, total runtime, number of simulations, and then I figure out what the number of SUs is. And now me as a reviewer, what I would think is, okay, I look at the biggest chunks first, 240,000 and 96,000. Does it make sense? Does the simulation time make sense? In your method, whatever you put there, whatever code you want to use, an experienced reviewer will know that what method, if that method scales out to those number of nodes or not, and based on that will scrutinize your scaling data accordingly. And then you look at the small bits here, and you can kind of, as a reviewer, follow if that makes all sense. But you can kind of see simulation time, number of nodes, total runtime, number of simulations. If you multiply that all out, you get some time of some number of SUs. Yeah, next important point, and this is already in my example here, if you do molecular dynamics or something where there is the use of community codes and well-known codes. Scaling for these codes is often well documented. Now, nevertheless, you have to document the scaling yourself. You do that to demonstrate the scaling for your specific setup. Community codes often cover a wide range of setups, and they don't all apply. Reviewers want to see what you did for your specific setup on that specific machine. David, let me get back to you in a second. They want to see what the scaling on the target machine is, or a machine with a very similar architecture. And the last, that scaling is so important because you will use that to accurately estimate the request size in terms of SUs. So with community codes, it's not enough, oh, everybody knows NAMD, I don't want to go into the details, just give me 1 million SUs. That is not going to work. You present scaling for a typical case again. You use the results to estimate the SU cost. Do not refer to external documents where scaling for your application is widely documented. You have been a reviewer before. If somebody in a proposal asks me to click on a link and then read through another paper, I'm not inclined to do that. It has to be all in one document. Reviewers want to read about your experience, and that will assure them that you know what you're doing. Yes, what to do? What if your required simulation time depends on the results of a previous simulation? Yeah, in that case, you have to make an argument for how you want to go. But if you just always go for the worst case, then the reviewer will figure out, oh, this is just inflated. So maybe it's a better approach to find some middle ground, and then to argue if the follow-up simulations need less time than I estimate here, then I will do this additional science. And if they take more time than I estimate here, then this sub-project will not be completed during this award period, and I will apply for the appropriate number of SUs in the next year. But there's no cookie cutter advice that I can give there, except for not just arguing always for the worst case, because reviewers will not buy that. Just argue in a more upbeat way. If I don't consume all the time, I will do extra science. And if I need more time, my project will spill over into the next allocation period. Additional considerations. Oh yeah, 2 slides on that. Your request may not be about just compute as use. The first thing that comes to mind is, of course, storage, either long-term on tape or medium-term on disk. And then sometimes a special requirement is a special queuing demands, what I had before for weather forecast, where you need a quick turnaround time. I think we all understand that that is only for very well justified requests. It is not that, my project is so important, I need all the time that I get, and I need to burn through it in the first quarter. That would not be categorized as well justified. It is also a good idea to disclose any problems that you may anticipate. The reviewers will not ding you for that. The resource providers, they are happy to work with you before you cause any trouble on the problem, so on the system. So it's always a good thing to discuss that in the proposal, and the reviewers will say, oh, I really like this proposal. They outlined a few problems here. I refer to the resource provider to get in touch with the user to work this out and to see how to find a feasible solution. And you should always discuss bottlenecks that you may anticipate, I/O, because you may overwhelm the file systems and that will get you blocked until that is fixed. So it's always a good idea to put that already into your proposal. Sometimes it's also file transfer from one resource to the other. And additional resource considerations are here. Whenever you have done something to understand the performance of your code or the performance of your workflow, or if you have done code optimization or profiling, anything that you have done there, a little bit of bragging goes a long way. Reviewers like to read about that, because when you read as a reviewer that a PI has done something to improve performance, it enhances the chances that the reviewer will think, the PI or the team knows what they are doing. They have done things to improve performance, to minimize the number of SUs. So I always encourage anybody to write about these efforts. They are usually very, very helpful to reviewers. And that leaves me already with the summary here. Design your proposal around the computational plan. Demonstrate efficient use of the resources through scaling. We all know that it is a proxy, so it doesn't help in your proposal if you start moaning about, but scaling is just insufficient. We all know that. Use that data also to do some basic math to estimate the total SU request size. Be reasonable. Here I point out with your request size, but basically with everything, ramp up over time, except that there are many, many other groups who will compete for the same resource, and in some sense it is a tough competition. It is a little bit different than when you compete for money at with the NSF or NASA or other organizations. Here, all positively reviewed proposals will get funded in some limited fashion. So it's not an all or nothing approach. And the bit of effort that you put into your proposal really goes a long way. And that leads me over to questions. And I saw that Ying has a question. Oh, yes, memory. Yeah, that's an important point. Maybe I can find that. Yes, this slide here. Or the time on the smallest number of nodes that is feasible. That is often done when your problem doesn't fit into the memory of a single node, but you need 4 nodes or 16 nodes to get started. So of course, you have to keep that in mind as well. And yeah, any more questions? Maybe in the chat room, or maybe somebody wants to unmute and speak up. That would be all fine.
Hi, I have a question about GPUs. So you sort of answered my question before about the number of GPUs, but I didn't explain it super well. It's kind of a subtle case where in biomolecular simulations you can do these sort of multiple Walker simulations for bias methods like metadynamics and things, where you need a certain number of GPUs at the same time for the methods to make sense. But then they all scale as the more GPUs, the less time the total computation takes. So then for the service request, are we sort of doing the minimum number of simultaneous GPUs, or in terms of the service request, it's just saying these are the total number of GPU hours I need, and then the queue will dictate how many GPUs I get at once?
Yeah, I think I understand your question, and I understand the subtlety. So from your, yeah, in this case, not scaling, but when you describe how your application works, you would say, I do a single calculation and I need 4 GPUs. That is just the canonical way of how this application works. And so your number of nodes, or in this case, number of GPUs, would be 4. And that 4 goes in here. And now the total number of simulations, that would be how many experiments you are running. And then you could add a bit and say, okay, if I ask in a job not for 4 GPUs, but for 16 GPUs, then I kind of advance 4 simulations at the same time. And if I understand you correctly, they are not coupled, so the scaling is kind of ideal. And so then it wouldn't make any difference in the outcome here of the total number of SUs.
Thanks, that makes sense.
You know, whatever, you know, for all the rest of the in the audience, if your code does, if you do not need to demonstrate scaling because there is a canonical number of nodes, a small number of nodes that you need to use, or a small number of GPUs, then you outline that in your proposal. Like you would say, my calculation on the GPU always uses 1 GPU, and you could, and then you go from there. If you are not on a GPU and you say, my code, for my experiments, I want to run all my experiments on a single node, then you would present some scaling on a single node to convince the reviewers that you know what you are doing. If you can argue my single calculation on a single node needs all the memory of the node, then there's of course not even a choice that you would have. If you don't need all the memory, you could argue, I run 1 experiment on a node for a certain time, or I run 2 experiments on a single node, and each is limited to half of the course. And there you would argue, hey, this is the best and most efficient setup that I could find.
So I had another question about in terms of which GPU resource to go, or let's say you know, because Bridges, I think GPU is kind of small with the 36K80s or the 2x16K80s. In terms of which resource, so like my startup was for Bridges GPU. Sorry, my startup is for Bridges GPU, but it seems like basically because there are so many different resources, and you might have different scaling things, would it make sense to request to test my code on the different GPUs to see if I'm getting better performance with the, you know, 4x V100s versus the 2x K80s? Or does anybody request time on multiple GPU resources? How do you sort of, any thoughts about that?
That is difficult to answer, but the first part of the question is, do you need single precision GPUs or double precision GPUs? So if you only need single precision, you should not ask for double precision, and of course vice versa, but vice versa, nobody makes that mistake, of course. And then between the GPUs, I'm pretty sure you have run your code in your own lab or on other resources, so you have an idea if the K80s or the V100 are better, so you would target in your startup one or the other, and if you're unsure, then you target both. And then in your proposal, you could discuss the performance of both, or you could also, you know, after a quick test, you figure out, no, the K80s work better for me, and then you kind of forget about the V100s in your proposal, and you would write a proposal that is just for the K80s, or vice versa if you think that the V100s work better for you.
Okay, and I guess I can check this, but like the V100s are clearly faster, but they're going to be more service units per GPU hour, right? And that, so if there's, let's say there's a 30% speed up on a V100, maybe that does not warrant the request, or I could still just put both of those numbers in the proposal to say, so I want this many V100 hours and this many K80 hours, or maybe that's too subtle.
Yes, you can of course argue for both, but that goes back to a point I had on an early slide. Do not target the same resource twice. So I would say, unless your request is super big, you would decide in your proposal if you want the SUs on the K80s or on the V100s.
But this is something, if for practical reasons, say I have one enormous system where the speed up on the V100, one replica per node is a lot better, then I would need to specify that beforehand, right? Like it's not just once you have your SUs, you can spend them as you need. So I would say if I have a system that is much better running on 8 V100s at a time, and I can justify that efficiency, that needs to be upfront in the proposal.
Yes, I mean, you touched on something that is, of course, always there. Once you have the SUs, technically you could argue, now I can use them any way I want, unless, and that is true up to the point when you write the renewal for the next year, where you have to put in a progress report, and you have to convince the reviewers that you did in the last year what you promised in your proposal from previous year.
So,
but in your case, I would argue you figure out, are the K80s better all around, or the V100s are better all around for what you want to do? And then you target one or the other in your proposal.
Yeah, I mean, that'll be math, right? The V100s are always faster. It's just whether the speed up justifies the larger number of service units.
Yeah.
So we'll have to figure that out.
Yes.
so this is Ken. Let me not, I hope I can uncomplicate, or maybe I will complicate. So there'll be an announcement coming out very soon. Bridges 1 or the Bridges machine is going to merge to a Bridges 2 system in the fall, which will have no K80s or P100s. It'll be all V100s. So it's something to think about. But you can't test on the machine yet because it's not in place yet. And that'll be the same for the Expanse machine that's coming to San Diego. So the Comet machine will still be around through late winter, I think, in 2021 with the K80s and the P100s. But that will also go decommissioned. So it'll be all V100s and going forward.
But there's always a next generation. So there are always multiple generations of GPUs available.
Yes.
And you explore one or the other or both, and then you make your pick.
Right.
There's a question from David about the memory usage and efficient memory usage. Is that important? My answer is no. You use, if your code doesn't need much memory and a node has 192 gigabytes and you only use 20 gigabytes, no, you're not dinged for that. So in your specific case that in the beginning you need to use 50% more memory than during normal runtime, I mean, I assume that is all in one job. So then you have to have a minimum number of nodes that supports this extra memory footprint during the setup phase of your program.
On that question about memory also, there are some sites that have a larger memory available per node. So Comet has some nodes that are 1.5 terabytes. Bridges have some that are as 3 to 12 terabytes per node. So if you are running into issues with memory.
Yeah, but Ken, and that's a very good point. I should add that to my question, to my answer. If you talk normal nodes,
Right.
no, the memory doesn't, the efficiency on the memory doesn't play a role. But once you are asking for large memory nodes, which are much, much more expensive than normal nodes, then you have to present a reason why you need all that memory, and you have to convince the review panel that that is really justified.
Right.
These nodes with terabytes of memory are, of course, by an order of magnitude more expensive than the normal nodes.
Correct. Yes, there are much less available of those than there are of the normal nodes. But many of the new resources coming in will have much larger memory per node availability. I think double on most of them, at least for Bridges 2 and Expanse.
Anything else? Yes. Yeah, if the baseline is dedicated by the memory requirement, yeah, that would be your justification for the baseline. That would be here, where is it? Here, you would say, okay, for the test case that I'm going to present my scaling for, I need a total memory of a terabyte, which means I need at least 5 nodes. And therefore, my scaling plot doesn't start at 1 here, but it starts at 5. Yes, I had comments from the reviewers questioning my baseline numbers, especially for jobs smaller runtime estimate. Oh, Ying, maybe you can unmute and explain a little bit what you mean.
So like the comment specifically was questioning why, for example, I'm using this number of nodes, even if the runtime is only for 10 minutes. And they said, for example, the applicant could use like a lower number of cores to increase the efficiency. The issue that I have sometimes is maybe the baseline was a little bit too high, and it would seem like we didn't start off where we should have started off.
Your baseline was dictated by memory?
Sometimes for like the jobs that we're running with Berkeley GW, it's for a big system like the ones that we're using.
Yeah, then you should present scaling plots for not just one typical case, but for multiple typical cases. So that you can say, for the ones that really don't need all that memory, I just want to run on one node and I run for 60 minutes. And on the ones where I need more memory, now I have no choice but using 6 nodes, and then it runs only for 10 minutes.
Wait. So the question though wasn't about like applying the scaling information to different problems. Is like how to justify the baseline, so that the number of nodes that we use. Because I didn't. Mhm.
If your calculation is short, then your baseline should be the smallest node number that supports the memory footprint that you need. Because, I mean, if your job runs only for 10 minutes, there's a significant overhead to spin up a 10-minute job. And therefore, it is much more efficient to cut the number of nodes by 4 and then run 4 times longer.
Right. And like, what if that's the best that we could do? Do we have to justify it in the scaling information document?
You mean that's the best you can do because you need the memory? Yes, then you have to say yes. Then you do this argument, or the time on the smallest number of nodes that is feasible, and feasible in your case means memory footprint. But if your calculations are that short, then you should say, and then I run back to back to back multiple simulations in a single job. So that the startup cost for each job is, amortizes.
Okay. Even if they're from different projects, like should bundle them up. Like sometimes you just need to run just this one short job.
No, I mean, in your proposal, you outline what you try to do. Later on, if reality doesn't fully match what you proposed in your proposal, okay, that's fine. I mean, in the proposal, you are describing a more idealized situation. So now there's a little bit of bending of the truth there.
Okay. Well, should I justify this requirement in the main document or in the scaling information document?
Now, the scaling document is basically the hard facts. But in the main document, you put all the numbers back together. You say, hey, from the scaling document, I select I need 4 nodes, and this is my time. But the basic math and everything, that should be in the main document, right next to the table where you outline your total SU request.
And this includes the memory, just the justification for the baseline.
I mean, that argument should be in both documents. In the scaling document, you say, for some of my experiments, I need at least 4 nodes because of the memory requirements. And then you say, and there's no reason to go even to 8 nodes, so I picked 4 nodes. And in your main document, you kind of repeat that argument why that is only 4 nodes.
Okay. And if we don't provide the justification for the baseline number, then would it be safe to assume that we should start doing the scaling information from 1 node, 2 nodes, something like that, rather than like 6 or 10?
Yeah, if you're not starting from 1 node, there should be a sentence why.
Okay. All right. Thank you.
Oh yes, there is a question about local scratch storage. Do you want to unmute and ask your question? Because I'm not sure, local scratch storage, you mean on a Elastic file system or local to the node?
Hi, I'm talking about, scratch storage local on the node.
Yeah, there are some large memory nodes, I know at least in Pittsburgh, that have large scratch storage. So if you don't need the memory of the large memory nodes, and this is your only requirement, then I think you have to convince the reviewers that the performance is actually so much better on local scratch storage compared to Lustre, which I highly doubt that that will be the case.
Right.
I mean, you only really need local scratch storage if you are creating millions of small files, something where Lustre is not very good at.
Okay, thank you.
But if you would work on a few large files, then your Lustre file system is of course much faster than any local storage. That's kind of what Lustre is good for.
Okay, thank you.
You're welcome. Any other questions while Paul and Ken are talking about V100s on bridges?
If there are any questions once the session ends, you can always send email to help@exceed.org, and these will get to the appropriate group, whether it's allocations or it goes to the ECSS staff or to the particular sites if you have a site-specific question. The groups are always very good about answering questions quickly. If you mention that it's something to do with the submission of an allocation request, it'll get to my group, and we definitely can discuss it and also get any expert that's needed to work with you on that. So if there are no further questions, oh, there is a question there.
Oh,
David.
for David, no. The answer is no. For startup allocation, you do not need any scaling data. The startup is for whatever you want to use it for, either to produce scaling data, or some people want to just install the code and see how it runs, or if the Exceed environment is good for them. So the answer is no.
Right. And David, if you're submitting that for preparation for a research request by July 15th, please make a note of that, and we definitely will work to expedite that so you have enough time to do the necessary testing to prepare your documents. Okay, well, Lars, thank you very much. Everyone that stayed on and joined us, thank you very much. I think this was a nice session. Hopefully you've acquired a lot of good knowledge of what's expected in a code performance scaling document and also in the main documents and all. I've had some great questions. Appreciate those. And again, if you have questions going forward, send email to help@exceed.org. And again, we'll be happy to answer those. Look forward to seeing some proposals from y'all. And hopefully some great research evolves from that. So again, thank you, Lars.
Thank you very much.
Thank you very much. Y'all have a great day. Stay safe, be healthy.
You. Bye.
Take care.